didn't, it was just not on my person for a while. So, yes.
Are we allowed to ask you questions about our test, like not now, of course, but like later on?
We can talk about it openly. Everyone's taking in all the grades are in.
We can.
Yes, I was
You
going to
mind
start with
asking?
that.
Oh, sorry.
Go. That is to say, please go ahead.
I liked it more than the homeworks.
Yeah, I custom picked and tailored the questions specifically myself. So, brief forward, hello everyone. Test was had last week and it was very good. Everyone did very well. I have, now that the grades are in, I have since changed WebAssign so that it should show you my new updated score for you. That said, WebAssign's not designed to work like this. There's 110 points total, and I'm grading out of 100. So the percentage WebAssign gives you will be wrong, because that will be 110 out of 110. Look at the number of points, which is also the number that I gave you in the email. So the email specifically lists, points out of 100, the final grade, which means it's possible to get 10 extra bonus points. And it lists some pointers about some specific questions. If I didn't say something about a question, it means you got it completely right, nothing to worry about. If I listed something about a question, it means that there was something. It might have just been one tiny units thing, it might have been something else. And we can begin to get today by looking at those, looking at the test, answering any questions you have, because this material will be important for the exam.
Bless you.
Thank you.
Bless you. So yes.
On number 7, on E, when it had like A, B, C, D, and
Yes.
A, how did it need to be method?
So, and I did not take many points off for this particular part. It was like maybe 1 point at the end for the signs. So if WebAssign is telling you, oh, you got this wrong, it doesn't mean you lost all your points there. I probably give you most of your credit back in my modified scoring. To try to pull up my version of the assignment real quick. I love days with Wi-Fi. If you've looked at WebAssign recently, your score should be visible, and I have not made live the Chapter 15 assignments yet. Why is that not? Oh, because I'm not connected to the thing, that's why. The Chapter 15 stuff will go live today, and it will be due next Tuesday. We're going back to 1 a week.
For lab today, are we like meeting actually in person, or do we just do the simulation?
So, there's many announcements today. We will talk about this, but since you all went ahead and asked, the Chapter 15 assignments will go up today. We're going to start talking about Chapter 15 today. And Chapter 15 is beginning the core of the class about electricity and magnetism. So this is the second chunk. This is what starting from now until the next test is going to be the next batch of material. And we're starting with electric fields and Coulomb's law, which are very, very hard to represent visually in a lab space, unless we have very sophisticated equipment. I can talk about electric fields all day, but all I can really show you are flat images on the screen. It is rather hard to physically represent them super well. So, I did say at the beginning of the semester, labs are going to be kind of a week-by-week basis, depending on what our experiment is. This week's lab, we do have one, but it will be, the assignment will be available online, because it's going to be using simulations. you guys still have the option of coming to the lab room, because I will be there helping you with the simulations, answering questions. But the document that I've gone ahead and uploaded to Brightspace, I've already put the lab file there, and it's links to the simulators. It's on they're from a website and service that I use very frequently. They're easy to use. You just drag elements around, and all the physics around them changes accordingly. And I just feel like this would be the best way for us to represent the electric fields of what we have on hand. And also, we just had a test, so a nice not having to show up if you don't want to lab, I think, is nice. So, we'll absolutely talk about the test, but since that was already asked about, just as a brief calendar glance, I guess the report up there. Wonderful. So, this is the first week of March, which is overlapping with this piece here. This week, March 1st through 5th, we're starting chapter 15. We'll have a lab based on that material, but it is online. You can still work in groups, absolutely. You can work together either outside of lab, or you can come to the lab time, and I will be there to answer any questions you have. You don't have to, though, if you just don't feel like using a simulator in the lab room. Yes?
So is there like a worksheet that goes along with it?
Yes.
But that's online?
Yes. The document is online. You can go ahead and look at it. The document has links within it to these simulators.
So do you want us to come and like turn this in during our lab time?
You do not have to turn it in during your lab time. I'm going to say that I would like everyone's copy to be turned in by the end of Friday, so that I can bring it over the weekend. And I can, if you do it digitally, I know a lot of you guys have been writing on notes and documents on tablets these days. If you want to turn it in digitally, do it digitally, hand it in digitally, you can just email me the document with everyone's names in it. I'll also accept it for copies if you prefer it that way. That's been a lot of announcements already today. So, brief review. We will look at the test. So we're going to start with the test today, and we'll make sure everyone's questions are answered before we begin chapter 15. This week, we are starting chapter 15, which is the beginnings of electricity. We have a lab this week that is, the document is online because there's multiple simulators. You can do it without having to come to lab if you do not wish to. And next week, we will be moving on to chapter 16, and we'll be continuing with, I'm planning, in-person electrical-based labs. So this week is another one of those exception weeks. We'll resume as well next week. Also, chapter 15 homework and quiz will go up today. They are slated to be due midnight, the end of Tuesday the 9th.
Our next test is like April. No. Yes.
I believe so, yes. Because this is going to be a chunk of like maybe 5 weeks. Because I would rather split along like sort of theme lines than split along an even 4 weeks, 4 weeks. Because all of heat and thermo and then a little electricity would just make me angry. Like if I was taking this, I would be thinking, this doesn't have anything to do with the rest of it. I don't want it to be here. So that's how I set it up. That said, just because there's more weeks between this and the next test doesn't mean the next test is going to be long enough. Speaking of tests, all the way back to the first thing I was asked today.
Sorry.
It is okay. There's a lot of things to cover, and you guys all have very good and reasonable questions that come up at various intervals. That is fine. So, looking at specific testing for you now, this is test question number 7. My numbers won't match yours completely, but all the methods are still the same. This particular question, we were looking at the cycle of a heat engine. So this graph represents the different stages as a piston is expanding, contracting, heating up, cooling down. And each of the parts of the question, we were looking at a specific part of that cycle. There's one wording trick, which ultimately resulted in just a couple of points worth. The whole question was worth 10 points, and you would lose like a maximum of 2 if you didn't get these signs right, just to give you some point spread there. The question asks, find the work done on the gas along the paths A to B, B to C, C to D, D to A, and then throughout the whole thing. So when work is done on the gas, something else is likely pressing into it and its volume is contracting. When a gas does work, typically it is expanding and pushing out of itself. So along these paths, A to B, the volume increases, it should be doing work out of itself, meaning that the work done on it would be negative.
But the work it does.
Right. The work the gas does is positive. The work done on the gas is negative. Again, that is worth like 1 out of 10 points if you didn't get the sign right. No matter what WebAssign tells you, WebAssign will just say question wrong. The professor says you only lost 1 out of 10. Just because it's a minor thing. I'm looking mostly at the math. Steps B to C and D to A are both going to be 0 because there's no volume change those entire times. You can't have a negative 0, so pretty much everyone got the zeros right. C to D, the volume is decreasing, so work is being done on the gas, so the answer there would be a smaller positive number. And then the whole cycle, A, B, C, D, and then A again, you want to add all the previous steps together. And I did not take any points off here if the number was wrong because your signs were wrong. I gave you full credit for this chunk here as long as you literally added all the previous ones together, whatever your answers were.
Wait,
Yes?
so like, for the email you sent me, you talked about number 8, but I got number 8 right.
Oopsie.
But like, wait, I don't like, are you talking about number 7 or are you talking about number 8?
Let me check the email because I wrote a lot of these in quick succession and I copy pasted some things. Yes, that is talking about 7.
Okay.
I apologize.
Okay.
That one's on me, and then I'll do these very quickly.
So because our first number is greater than 8, that would also be our.
Correct.
Okay.
Again, very minor thing. You can make this mistake and still get over 100%. That's why this is basically the bonus points mistake. One of them, at least. And again, this is also why I give you more than 100 points for it. It's act as a buffer against tiny things. But yes, you want this machine to be doing work out of itself. So you would hope work done on the machine would be negative. You want it to be doing work in the other direction. Most machines, you hope that's the goal. Let's see. Any other specific questions for you guys? Okay. And again, everyone did very well. Like, y'all did a very good job. You are good at physics. Congratulations. I mean, that's faith-based. I'm proud of all of you. And so I'm completely comfortable if we sort of close the book on this first chunk and now begin focusing on the second chunk. Because just knowing all of your backgrounds and the classes you're likely taking, this whole first piece here has been like triple review from your previous science and chem classes. Electricity is probably something you might be a little fuzzier on. And so that's one of the reasons why we're going to be spending more time on it. It's also just harder to conceptualize, especially in the organic fields. So I am completely comfortable with you guys on all of this material. I think even on the exam, coming back to it, it'll be just fine. So unless there's anything specific you guys would still like to talk about, we're going to switch gears and begin electricity magnitude. Oh, I have not. Yes, I did write the chapter 15 minutes. Oops. They are, this is a slightly old copy. I still need to modify things slightly when jumping slides around based on the changes I'm going to make eventually. You can see it's just slightly out of date. But the material is all accurate still. We're going to begin looking at electric forces and fields, and we're going to start with some review again, coming at this from a slightly chemistry perspective. Electricity happens largely because of these things. You've dealt with all these particles in your classes before. This table's in the notes just as a reminder of their physical constants. Every single particle is made up of some combination of these things, and protons and neutrons, they live in the nucleus. They are orders of magnitude larger than electrons, and yet neutrons have no charge. Protons and electrons have an equal magnitude of charge, but opposite signs for their charge. We have the charge values listed here, and the relative mass of each particle as well. So this table exists for your reference. And we define electricity as moving electrons, because out of all of these particles, they're the ones that are actually able to move freely. Because neutrons are neutral, so they wouldn't really move due to electricity even if they could. Protons are charged particles, but they're stuck in the nucleus, so they don't tend to go anywhere under most circumstances. Electrons, meanwhile, are charged, they will react to the electric fields that drive electricity, and they are free floating. They can leave atoms under the right circumstances. So if I was to give a blanket statement for electricity, it is the movement and net flow of electrons. And minor thing that people don't often talk about, electricity is moving electrons. You need electrons to move from point A to point B to generate electricity. It's the literal movement of those charges that creates it, that is it. And the individual electrons have mass, which means that a bolt of lightning has mass.
So it's like flying?
Basically, it's particles that are just being pulled from one place to another because of electric forces, which are stronger than gravity. So, on a stormy night, when a bolt of lightning hits something, if you could pause time and take that lightning bolt, you could put it on a scale and weigh it. Which I've never seen anyone else talking about. It's very strange conceptually, because we think of electricity as energy, but the actual physical electricity is just the moving electrons. Those electrons just happen to be particles with mass, and when mass is moving, it has energy. So electricity is a physical phenomenon that just happens to carry energy from place to place. Electricity itself is not just moving energy. Whenever you see lightning, I'm going to go ahead and draw a lightning bolt because I'm going to be referring back to it a couple of times today. Thank you. This is going to be a poorly drawn tree. A poorly drawn thundercloud. Well, I realize the only difference here is one of them has a trunk. Cloud. Tree. Bob Ross land. And lightning. So, we've all seen electricity, right? You've created static sparks, you've seen lightning storms. What you are seeing here is not literally electricity, the actual thing that you see when this happens. Because the electricity is moving electrons. Have you ever seen an electron? Not with your human eye. What you're seeing here is air. Electricity carries energy from place to place. It is the physical moving electrons. And as those electrons move through something, because they are matter colliding with particles as it travels, it leaves energy behind. These light bulbs work because electrons move through gas in tubes, leaving energy behind in the gas. And when that gas has energy, it kind of spot turns into plasma for a second and emits light. So what you're seeing here, this is really the same phenomenon as a light bulb. This is just hot gas fluorescing for a split second. Which is why you don't get lightning in space.
Wait, because there's no air?
There's no air. You can still get a lot of charged particles in space, and a lot of hot gas, but only in and around stars and nebulas.
So is it the electron that electrocutes someone? Or is it the hot gas that like burnt them?
So this is hot gas because the electricity is traveling through air. Electricity always needs something to travel through. It needs a conductor. In this case, it's air. In the wires, it's metal, the metal wires themselves. If you were electrocuted, then you would be the conductor, meaning the electrons are surging through your body instead of the air. And as the electrons travel through whatever part of you they are in, they will leave energy behind in those particles, roasting you from the inside. So, don't shock yourself. Pro tip. As we go on through these chapters, I'm going to be giving you more tips on best ways to not get electrocuted. Or at the very least, not get electrocuted fatally, if you can't avoid it.
Wait, so it's electrocuting the air, right?
This, lightning is yes.
Yeah.
Lightning is just air being electrocuted. Yes.
So why do people say like you never, like lightning never strikes the same place twice?
Good question. That's ultimately because of these things. So, I've been kind of brushing over the differences between the particles because I assume you've done work with these before. Is that a correct assumption? Is anyone not comfortable skimming over these particles in the whole? Okay, we can revert back to them. We have the table, I can talk about them anytime. But, because the electricity is moving electrons, when something gets struck by lightning, it suddenly becomes highly negatively charged. In the moment that it's negatively charged, other electrons don't really want to go there. So in that moment, like right after the strike, when the tree is flaming and still full of electrons, lightning's not very likely to hit it in that moment. But eventually, after it discharges all those extra electrons into the Earth and it becomes neutrally charged again, this tree is just as likely to get hit as anything else. So lightning never strikes twice is complete hokum, because there's a park ranger who's been hit like 7 times in his life.
I was gonna say, because
Which A, proves bad luck does exist, B, proves good luck does exist, because he's still alive, and C, proves it can strike multiple times on the same place and the same person. Yes?
Like, what's the difference in like lightning strikes and like heat lightning? Because like when it's like not like a necessarily like bolt, and it's kind of like a flash.
It's still electricity moving from place to place. Heat lightning, I'm less familiar with, I just haven't researched it super closely. I'm under the impression that when air is super hot, it tends to shake more of its electrons naturally loose, which is, basically it's on its way to becoming plasma, which is a charged entity. As it shakes its own electrons loose, they're just naturally trying to surge somewhere. And they just don't want to be on the particles that got rid of them. But because now those particles are positively charged, you get a return stroke where electrons surge back to them, because now that's the positive place to go, which is why most bolts of lightning have what's called a return stroke. You got the arc down, but now this is negative, so now they want to go back up towards positive.
What? You lightning up?
Yes, you can lighten up.
Okay, but so where are these electrons coming from? So the cloud has electrons that are, what, like very charged?
Like every electron is functionally identical for the sake of the universe. Every electron we talk about is going to be the same as every other electron. What happens up here is this cloud is probably next to a bunch of other clouds. And on a good day, they're all neutrally charged and just full of electrons and protons in equal measure. Because to be neutrally charged, you need the same number of both. But there's this thing called charging, where you can force one object to have an uneven number, making it either more positive if it has more protons, or more negative if it has more electrons. And the most common way to do that is just by friction. This has happened every single time you rub your feet against the carpeted floor, anything involving a wool blanket, anything involving the plastic playground equipment when you were a kid that made your hair skyrocket upwards. Charging via friction is simply, the particles of one thing are colliding with the particles of another thing, kind of like how thermal energy works. And in those collisions, electrons literally just jump from one atom to the next. And as this cloud frictions against other clouds, it can literally just absorb a bunch of electrons from other clouds and then hold on to them. Just depending on what cloud touches which other cloud for any length of time. Which means after a while, this is just going to develop a huge negative charge. And none of those electrons want to be anywhere near each other. Because colloquially speaking, negatives repel negatives, positives repel positives, but positives and negatives attract. So all these negatives up here, because the cloud has just been rubbing against other clouds and generating that total charge, a total negative charge, these electrons just want to get out. And so they will leap to the next closest, next positive thing that they can, which is usually tall, pointy things.
So like, okay, tree is electrocuted. Don't touch the tree until it is rid of.
At least till it's not on fire. Odds are it'll discharge itself pretty quickly. The main issue is just that it's going to be burning and falling.
So like, so the size of the lightning is dependent on how many electrons were like negatively charged coming off of the cloud?
Yes. And I'm going to show you some math now, because I realize I have not given you any new slides to write down. So if you've been transcribing all the things I've been saying, great, but I'm now going to make sure you have some actual things to copy to you in your assignments. So, this is the first formula we're going to be talking about, and this formula is the reason that all of this happens. This is the math behind why everything electrical happens at its core. This formula is called Coulomb's law, named after a, I believe, French physicist, is it Justin de Coulomb or Augustine de Coulomb? And the formula reads as such. The force, and I would modify this to say the electric force. I tend to do F with an E subscript for electric force. Between any two charged particles, or any two charged objects, is equal to K, which is a universal free constant that will be in your notes and formula sheets. This is the electrical constant, Coulomb's constant. Yes? Yes. And you know what? Myself, add a few notes. So Fe is electrical force, and it is literally a force. It is measured in newtons. So this is the literal force between two objects, measured in good old-fashioned newtons. Anytime you have two charged objects at any radius from one another, there's going to be some force between them. This is the force that ultimately causes opposites attract, likes repel. This is the force that will either attract them or repel them. So this is ultimately the thing that makes all charged particles move ever. And as long as gravity is not the thing. So, Coulomb's law, that's the name of this formula, tells us that the electric force is equal to K, which is this constant, 8.99 times 10 to the 9th. This is just Coulomb's constant. This is a freebie. It's always going to be the same number. So we have Coulomb's constant times charge 1 times charge 2. The lowercase q's here represent charge. So Q, lowercase q in general, represents total charge of some object. And in order for there to be an electrical force between two objects, you need two objects. So the two q's represent the two different charges of the two different things. So I'm actually going to quickly.
And what? Do they have like a unit?
They do. I'm going to backtrack just slightly to go back to the fundamental particle page. So, on this slide, which will be available to you, as a fundamental constant property of these subatomic particles, they all have a known charge. This right here just measures the magnitude of the charge of that particle, and the unit for that measurement is C for coulombs. So Coulomb, the scientist Coulomb, named the law and also named the unit for charge. So I will also write up here, Q is charge measured in coulombs.
And that will change on particle to particle, or is it to know when it's positive and negative?
All protons, if it's a single proton, has this charge, 1.6 times 10 to the negative 19th coulombs. All single electrons have this charge. Notice it's the same thing, just positive and negative. Meanwhile, a neutron is neutral because, at least on some fundamental level, a neutron is literally a proton and electron fused together. So it just evens out.
Then why, why is the neutron weigh the same as a proton if the proton also has an if the neutron also has an electron?
It technically doesn't. A lot of people will, I was always taught that a neutron is slightly bigger than a proton. The problem is that the electron is just so tiny that adding its mass to the proton doesn't really change it that much. This is like the smallest unit of mass you will realistically encounter. This is unfathomably small, which is why when you get shocked, the weight of the electrons entering you is negligible compared to the energy they're pumping into your body. So, the unit for charge is coulombs. And this is the smallest unit of charge that exists. It doesn't get any smaller. This is the building block of all larger charges. And because one electron has a charge this small, you will never, in nature, actually be anywhere near a charge of 1 Coulomb. 1 whole Coulomb would be like a squintillion protons all by themselves. 1 negative Coulomb would be a squintillion electrons all by themselves, which there's no realistic way to force that to happen in nature because you would need the force of 10 supernovas to try to jam them all into the same region of space without any of the opposite particle.
So the charges should always be really small.
Charges will pretty much always realistically be hyper tiny. The most realistic large charge unit we're going to work with is microcoulombs. I know there's going to be some microcoulombs questions. I might give you a few questions with like 1 Coulomb in it, just to show you how absurd that would be. So 1 whole Coulomb, positive or negative, is just bonkers. But charge measured in coulombs, as a general rule, will always be hyper tiny, positive or negative. Oops. Okay, so force electric equals K times the charge of both objects involved multiplied together. As a reminder, in order for there to be an electric force between two things, you need to have two things, each with their own amount of charge in them, and divided by radius squared. This is admittedly a slightly different definition of radius, though. This is really just distance, but it's specifically the distance between the center of each object. Because that's the core of its charge. That's the spot the charge is concentrated in. So, and I will write this, R equals distance between the center of each charge. Doesn't matter if we're looking at single electrons, doesn't matter if we are looking at planets that have a net charge. You need to measure their center, from center to center.
Would that be in meters?
Meters, yes. It is a distance, so we like to use meters.
No, it'd be really, really small too.
Sorry, one more time.
Isn't that gonna be really, really small?
It can. If we were, say, if this drawing, say we're looking at 2 different electrons, you know, on adjacent atoms in your pinky, yes, that distance would be very small. The charges would also be very small. The net force would ultimately be very, very small. So we are going to be dealing with some kind of ridiculous numbers when we try out. Welcome to physics. Everything's either super big or super tiny.
Also, if you were gonna so if you were given F and you were trying to find R, or one of the charges, that can take a little bit of algebra, correct?
A little bit,
You
yes.
just have to multiply by R squared.
I would say the most difficult part of the algebra is just the fact we're going to be dealing with crazy exponents, and you want to make sure to keep everything aligned in your calculator such that it doesn't try to multiply the wrong things or exponent the wrong things. That, in my opinion, is the most difficult part of this, because there could be questions where every single one of these numbers has a times 10 to it attached. But this formula, this law, is the reason why all electricity ultimately happens. Because, say if we're looking at the lightning bolt again, there's a bunch of electrons up here. So this cloud, very negatively charged. This tree, probably neutrally charged, because trees tend not to really be charged, but it's more positive than the cloud is. So this is the next closest positively charged object as far as the cloud is concerned. So very neutral, very negative, slightly positive, radius apart. The cloud is just going to drift through the sky as the force created by this formula just keeps getting bigger and bigger as the charge builds up and as the cloud gets closer to the tree, until eventually this force gets so big it is literally strong enough to literally rip the electrons straight out of the cloud, travel through the air, and into the tree. All electricity is just because that force gets big enough to rip electrons from point A to point B.
Wait, and you said it becomes highly negatively charged because of why?
The cloud ultimately became negative because it was charged by friction.
All of other clouds, or others, they're just, okay.
We will talk about charging, how to do it later on. We're starting with this because it's the backbone of everything else. And to at least apply one tiny example that we can work on together real quick. We're just going to focus, okay, I've written over it now. We're quickly just going to focus on the first part, just to get some math in your notebooks. These are two electrons, although it kind of looks like a happy frog. These two electrons are 1 millimeter apart. What is the magnitude of the electric force between them? So, general order of operations, I'm going to rewrite our formula. F equals K Q1 Q2 over R squared. We are asked for the electric force. So, we want this. We're going to move forward finding this. So we need every other variable present. K is a given constant, so I'm going to go ahead and start filling things in here. K will always be 8.99 times 10 to the 9th. So that's a freebie. Next, we are told that these particles are 1 millimeter apart, so we know their radius. We're just going to assume that these particles are so small that the distance between particles is just the distance from center to center. Radius of an electron is a negligible number for all classes. So, we're going to square the radius between them. 1 millimeter will become 0.001 meters, and that this number will be squared. The last piece is charge times charge. And I said that these are electrons because the charge of an electron is considered to be a known constant. So the table from earlier on is free reign to consult for any and all things involving charged particles. So we can look back at this table. Charge of an electron is negative 1.6 times 10 to the negative 19th coulombs. Unit is coulombs. And they both have the same charge, so we're going to plug that number in for both Q's. Several problems will be given two different charges for two different objects, but in this case, they are just the same. that gives us every number to then proceed and find our answer. Off the top of your head, do you think this number is going to be very, very big or very, very small? Very, very, very small. Because we're ultimately squaring one of the tiniest numbers in existence. So, force will be very, very tiny. Which ultimately makes sense because it doesn't take a whole lot of force to move something with a mass that small.
What's the units for force?
Newtons. Still newtons. Any force will always be newtons. So, what is your tiny results thus far?
2.3 times 10 to the negative 22.
Okay, everyone agree? Okay, very good. So, incredibly small force, like a factor beyond a billion times smaller than 1. So, super tiny force, but to at least conceptually look at the second question on this slide, that super tiny force is acting on super tiny masses. So the acceleration of a single electron from a force that tiny might still be pretty noticeable, which is why electricity moves pretty fast. But it's also why you don't feel it. You don't feel electrical forces on a normal basis because you are neutrally charged and because the individual forces on your individual particles are super, super tiny. It's only when a bunch of them are moving in the same direction at once that you finally feel something. Yes?
So how do we find out the acceleration?
That would be a very quick consultation of this table again, and a reminder of Newton's second law. Yep. The force we found equals mass of electron times resulting acceleration.
Did you do just one electron or did you both?
They both have the same mass, and they are both acting on, the same force is acting on both of them. That's a good question. This will be the last thing I mention today. The force created from this formula acts on both particles. They are both experiencing this number. What's funky though is, these are both electrons. So what direction is that going to be in? Outwards. Like charges repel.
Wait. Oh, the direction of the acceleration?
Right. Well, and also the force, because the force pushes them to accelerate. So the number we found here, just remind me what we found.
2.3 times 10 to the negative 20.
They're good, newtons. That force, note we got a positive answer, we would both like negative and negative. This force is acting on both particles, just in opposite directions. So particle 1 is being pushed with this force that way. Particle 2 is being pushed with the same amount of force, but that way. It's like reverse gravity. Gravity acts the same force on two things, pulling them together. This acts the same force on two things, but has the potential to push them apart.
So there, you could just do one mass because the acceleration is going to be the same
Correct.
for each one.
It's the same force on both. They happen to have the same mass, so they'll both have the same acceleration.
So a force doesn't have to be negative, right? Even if they're pushing outwards, like they were putting.
So notice that we got a positive answer. So the positive force in this case means repel. Hypothetically, if one of them was a proton, if this had the same charge but positive, how would that change our answer? Good. So
Wait, negative 10.
So the proton is positive.
if we had a 1 electron and a 1 proton, that'd be a negative times a positive. Our answer would end up being negative. Same magnitude, but a different direction. So as the general rule, do write this down, general rule, If this formula gives you a positive answer, that means repulsion. If it gives you a negative answer, that means attraction. And I've held you for quite a few more minutes. We will continue talking about this. We will revisit all of this on Thursday before continuing. Do be looking over your assignments and looking over your digital lab. Have a wonderful day. I will be in the lab room today if you have questions about anything. So just drop me an email or stop by.
So, do we do this lab by ourselves, or do we still turn it in as a group? Because doesn't that affect if we come all to the lab or if we do it by ourselves, like outside of the lab?
You can still do it in teams. I encourage you to work together on it.
Right.
But because it's virtual and online, I'm just not requiring you to do it in the lab room at the lab time. I will still be there though. You can still come in as normal and do it in there
You're
together.
gonna go to lunch?
You just don't
What
have
are you
to.
doing?
I don't care, whatever you guys want to do, 'cause it's not my only class, so I'm done. If we want to go to lab, we can, if we don't, it's fine. That's how we do it.
Wait, so what?
Me as well.
I kind of want to go to lab, just so I can ask questions.
I hear it over.
Okay, so just normal.